is actually a tertiary carbon. When we react it in a radical reaction, we get about, our majority product is right here at that tertiary carbon, because that's the most stable intermediate radical that forms. If I look down here, I have both. I can do the same reaction as here, but this time I have primary and secondary and primary carbons, right? In this case, I have 6 primary carbons, and I have 2 secondary carbons. Doing a little bit of mathematics, I predict that thermodynamically the radical here should be most stable, right? But I have 6 to 2 carbons, so if we do the mathematics and actually do the reaction, we do find out that in fact the secondary bromide is actually the one that's preferentially formed, even though I have 3 times as many primary hydrogens as I have secondary, and here I have 9 times as many primary hydrogens as I have tertiary hydrogens, just showing you that thermodynamically this is much, much more favored than using one of these, or the secondary is also highly favored over the primary. Yes?
So if we're asked to do that on the exam where there can be multiple products, but it's understood that the one that's more stable will be...
It depends on how the question's asked. Sometimes we ask major and minor products. Okay? This would be a major product. These would all be minor products. This would be major products, and then you'd have some minor products. So it depends on how the question's asked. Free radical reactions are not the ideal things to actually do synthesis because lots of other things happen. Okay? And the same thing's true here. 3%, it doesn't sound like a lot, but it actually gets formed, and then you have to separate these 2 compounds. If I wanted to make this one, 3% of this one is costing me a lot of money if I'm making those things. I don't want to make this and throw it away. So you actually then would like to find some better process for doing that rather than a free radical reaction. Even though reality 97% is really good for a chemist synthetically. That's really, really good. Okay.
So on the test, will we have to do the arrows?
That was last chapter.
So
You already got 12 points off for not doing that one right?
yeah.
Oh, that was mean. That was mean. I don't remember. You probably did that one right. But that one was challenging too. Okay? But whenever you're drawing a radical reaction and you're drawing reaction mechanisms, you're only moving 1 electron at a time. So if you're breaking a bond, you draw 1 barbed arrow this way and 1 barbed arrow this way. Always, again, starting from the electrons, moving either to another bond or to another atom.
So tertiary carbons are most likely to be reactive because they're most stable.
Because it's free radical. Once you get through the mechanism halfway, you form a tertiary radical, and it's more stable than a primary radical. So it preferentially, thermodynamically, that's the way the reaction is going to go, because it's a lot more stable as an intermediate. Okay. You had a question, Jacob?
No, she answered it for me.
Okay. Okay. Let's do this reaction. If I have this reaction and light, I'm going to form the bromine radical, and then I'm going to look over here, and I'm going to actually sort of pick off one of these hydrogens out here somewhere, and I'm going to add bromine to it. The problem is, as we found out in this last chapters, Br2 can also add across a double bond. And so we get this product that we don't want. We get the dibromide, and we lose the alkene. If I just want to put a bromine on this one here, I have to change my reaction conditions, and we have something special called MBS, which is N-bromosuccinimide. We just call it MBS. So in this case, if I take bromine, and I take some of this stuff, which is this thing down here, it actually slows the reaction down so much that I only react at these allylic carbons. I don't add bromine across the double bond. Remember that when I do pluck off a hydrogen from here, it's allylic now. Allylic cations, allylic radicals, allylic anions are more stable because I can draw resonance structures. Therefore, this is the lowest, this is the best thermodynamics, is actually add at this bond. So I literally add at that primary carbon to add 1 methyl group. And that's all because somebody came up with this reactant. They did a lot of research to figure that out, instead of just adding Br, when they added this into there, they got highly selective reactions. So in the test, if you're asked to add a bromine to an allylic carbon, you're going to have to put down that you have to use NBS in there with your bromine and light. Otherwise, you're going to get a lot of this reaction here. You're literally just going to add the bromine across the double bond. Because these electrons too are electrophilic or nucleophilic? No, nucleophilic. Because they're electrons. They want to attack something. Okay? There's not a positive charge on there. Okay? Good guess, Al. You had a 50-50 choice.
Well, and then you said, what are these electrons, and that confused me.
Yeah. Electrophilic electrons, nucleophilic is electrons too. Yeah. Okay? Okay. So what if I want to put a bromine up here? I know I have a double bond in there somewhere. So when I do form a radical, I put the NBS in there. My most stable radicals are going to be allylic to that double bond. So I'm either going to put a bromine there or a bromine there. My minor products will be bromines out here. And my minor products are being added two bromines across that double bond. So if I want to selectively put in a bromine right there, I have to use the NBS. Okay? If I look at this, once I form the radical, let's look at how we actually stabilize that, because I can draw resonance structures, right? If I look at this one here, I can actually move those electrons up to form a bond here, which gives me the radical down here, because I'm left one electron there, right? If I drew lines here, I draw one electron down to that one electron over to that, and one electron over to that carbon. That's how you draw it mechanistically to get a resonance structure. Resonance structures imply stability. They imply that you're going to have reactivity at that allylic carbon. Yes?
This is probably a terrible question. What does allylic mean again?
If we look at that, that just means one carbon over from the double bond. So if I look at, that's all it means. If we look at allylic, it comes from an old term when we talked about polymerization, because a lot of polymerizations happen at that allylic carbon, so they call it allylic. Let's see if we can do some reactions here. Show how a free radical halogenation might be used to synthesize this molecule right here. Well, if I look at that, I first have to draw it out myself. Okay? So what I do is I first draw out that molecule. Okay? So I actually use this name. I'm going to have a 1-chloro, 2-dimethyl propane. And then I can see, oh, all I need to do is get a chlorine here. Okay? Do I have any hydrogens that are tertiary there? No, that's a quaternary carbon, right? And so I have to pluck off one of those hydrogens when I form my radical. So I literally can just take that molecule, react it with chlorine and light and a little bit of heat, and I get that molecule via a free radical reaction. Yes?
I figured it out.
Good. Okay. How about this next one here? Let's draw the molecule again. I mean, you could probably do this one in your head too, but I can't, okay? If I look at this one, what I see is that I actually have now a tertiary alkyl halide, right? Because that carbon right there is bonded to 3 other carbons. I know that if I can get a radical to form at that point right there, that's going to be my most stable radical. So again, all I have to do is start with my base molecule, and I literally know that instead of putting a bromine here, 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 or here, my most likely place to put a bromine is actually at that tertiary carbon right there, right? Yes?
So if this was like on the test,
Yep.
would you, so if we got then, would you just give us the arrow and then the last part? Oh wait, just kidding, that's, okay,
The stuff in the red is what you have to come up with this
yes,
stuff.
okay,
Okay.
yeah.
I just drew this because I can visually see it. Otherwise, it doesn't make any sense to me. Yes?
Could you explain that first one again, please?
Yes. Okay. So if I look at this first one here, I need to come up with this molecule right here. 1-chloro, okay, 2,2-dimethyl propane. So here's my 1, 2, 3 carbons. I have a 2,2-dimethyl. Does that make sense? And then I want to put a chlorine out here on one of these 4 ends, right? Because there are no hydrogens here. When I have my chlorine radical come in, it has to react with a hydrogen somewhere, and there are no hydrogens in the middle, because it's quaternary. Now he's shaking his head yes. Is everybody else shaking their head yes still? Yeah, that's Gina.
So could it go on any?
It's a symmetric molecule. It can go on any one of them.
Okay,
There's actually 12 identical hydrogens on that starting material right here, right?
yeah,
And so any one of them could react with the chlorine radical to form HBr and my radical species on the carbon containing